Yes.
Yeah. Okay, great. Welcome back, everybody. I'm very pleased to introduce Nikolay Bazhenov, who will speak on equivalence relations on reals and learning for algebraic structures.
Okay, thank you. So I'd like to thank the organizers for inviting me to give a talk at this conference. So in this talk, I'll concentrate on connections of learning for families of algebraic structures to some particular Borel equivalence relations on the counter space. Okay, so Katya Fokin in her talk on Monday already gave some preliminaries on the learning for finance algebraic structures. But here I will introduce this in more details. So we fix some computable signature and consider a countable family of countable structures in this signature. Informally speaking, the problem of learning can be formulated like this. Step by step, we obtain larger and larger finite pieces of some structure S in our signature. So, of course, in the limit, we will obtain the whole structure S. In addition, here we assume that this S is isomorphic to some structure from our fixed class K. And the problem is whether it is possible to identify in the limit the isomorphism type of this given structure S. So Informally speaking, the problem combines the approaches of the classical algorithmic learning theory and computable structure theory. Summarizing, we can say that we want to learn this family K up to the isomorphism types. Okay, so before going into the formal definition of the paradigm, I will give a couple of informal examples. So what do we mean when we talk about learning some given family K? So for example, consider just a family K which consists of only two structures. These are countable undirected graphs, and the first one consists of cycles of size 3, and the second one consists of cycles of size 4. So, and we can learn this family via the following effective procedure. We have our input graph. So one can think of this as our graph is given a vertex by vertex. And when a new vertex appears, it immediately reveals to which old vertices it is connected and to which it is not connected. Of course, for a long, long time, it could be the case that all our vertices which appear in the input are just singletons. So, but anyway, if our input graph is really isomorphic to one of these two graphs, then at some point of time, it will be forced to show either a cycle of size 3 or cycle of size 4. And when the first such cycle appears, we already know what is the isomorphism type of the input structure, and we start forever outputting the natural guess. So if we see a cycle of size 3, then the input structure is isomorphic to the first graph. And if we see a cycle of size 4, then the input structure is isomorphic to the second graph. And note here that we do not care about other isomorphism types. That is, if S is not isomorphic to a structure from our class K, then we do not have any restrictions about the behavior of the learning procedure on this input S. So if the input structure is not from the class, then we don't care about what happens with this in the learning procedure. Okay, so this is the first example. And if you look at this more carefully, then why does the learning procedure succeed? Because these graphs are separated by existential sentences, of course, inside our class. So G1 has a cycle of size 3, and G2 has a cycle of size 4. So these two variants, each of these variants has its own existential sentence, which holds in this structure. Okay, and from this we go to a little bit more complicated example. Roughly speaking, if we remember the classical algorithmic learning for sets or for recursive functions, this is a delta 02 process. That is, it is limit computable. And the second example essentially is like this. The pair of linear orders omega and omega star, that is, this is the usual ordering of natural numbers, and this is the reverse ordering, or one can say this is the ordering of negative integers. So this pair of linear orders can be learned. And in a sense, this is delta 0, 2, because inside the class, again, these structures are separated or distinguished by EA sentences. That is, inside the natural numbers, we have a least element, and inside the order omega star, we have a greatest element. And so the learning procedure will will use this particular separation by EA sentences. So formally speaking, how can we organize a learning procedure, effective learning procedure for this case? So we have our input structure. We can always assume that it is isomorphic either to omega or to omega star, and it is given in stages. That is, we have an increasing sequence of finite linear orders. Okay, so we learn stage by stage, and at the stage S, we see some finite linear order LS. What do we do then? We find the current least element in the current finite linear order, and we find the current greatest element inside the current linear order. Of course, it is only for the current stage, because with time, the least element can stop being least, and the greatest element can stop being greatest. Yes, sure. So, and what do? We ask for how many previous stages, that is, the stages before the stage S, our current least element has been the least element. More formally, we compute the following counter, but this counter just computes the number of stages that the element ls stayed as the least element in the linear order at that stage. And we ask the same question for the current greatest element. So formally speaking, again, we define another counter. Okay. And after that, the current conjecture is really straightforward. We say, okay, if our least element stayed longer the least than the greatest element, then our guess that this element is really the least element, and then our guess is that our linear order is isomorphic to the natural numbers. And otherwise, that is, if our greatest element stayed longer than the least element, then our guess is that this is really the greatest element of the order, and our guess is that the isomorphism type of S is the omega star. Okay, so this is an effective procedure. And why does it learn these two orders? Because if our input structure S is really either a copy of omega or a copy of omega star, then sooner or later there will appear a real least or a real greatest element. And this element will stay forever, like really the least, that is from some point of time. From some point of time, ls will stabilize if it was the copy of omega, and if it was the copy of omega star, the element rs will stabilize. That is, in the limit, we will always output the same conjecture, and this conjecture will be a correct conjecture for the isomorphism type of this linear order, the order S. Of course, this is if we assume that it was really a copy of either omega or omega star. So there is this really delta 02 algorithm, which is based, again, let's go back, on the difference in EA sentences, which learns these two linear orders. Okay, so these are two informal examples, and if you have questions right now, please ask them. Yeah. Okay, so if there is no questions, I will proceed further, but of course, you're welcome to ask questions at any time of the talk. Okay, so these are two informal examples. And now we are ready to formalize the learning paradigm in the spirit of the algorithmic learning theory. We fix relational signature L for convenience, and here we again for convenience we only consider structures with domain omega. That is, the domain is the whole set of natural numbers. Uh, in order to make the things more convenient for the future, we fix some Gödel encoding, and now we can identify the structures in this fixed signature with elements of the Cantor space. Okay, so for convenience, you can think about these structures just as, say, directed graphs, and you can fix your favorite Gödel encoding, and then you can identify the space of graphs with the Cantor space. Okay. So we consider a countable family of countable structures. Here we assume that the structures are pairwise not isomorphic. And we need to specify four things: the learning domain, the hypothesis space, and what is a learner, formally speaking, and when we assume that a learning process finished or is successful. Okay. Before proceeding further, I should say that discussed learning paradigm, it appears, or it is based on, first there was in 1998 a monograph by Martin and Oscherson, and a more modern exposition was given first in the work of Fokina, Kurtzen, and Sanmauer, and then in our paper with Katya Fokina and Lucas Sanmauer. Okay, so what is the learning domain? Informally speaking, this is the things which we want to learn. Yes, so we collect all isomorphic copies of structures from our class K, such that their domain is the set of natural numbers. And as for our conventions, the learning domain can be treated as a subspace of the Cantor space. Okay. And what is the hypothesis space? It is these conjectures which are allowed to be output by the learner. And here, this will be just the set of natural numbers omega with a special symbol question mark. So learner M, it sees stage by stage finite pieces of data about a given structure from the learning domain, and at each stage it outputs a conjecture. A conjecture is an element from the hypothesis space. More formally, one can say that M is a total function from the set of all finite binary strings into our hypothesis space. And the meaning of these conjectures is kind of pretty straightforward. If we have some finite string sigma and the current output is I, then this means that this finite piece looks like an isomorphic copy of AI. This is our current guess for this particular finite piece of a structure. And for convenience, we also introduce this question mark. Sometimes we're allowed to output question mark, and then this means that right now the learner M, it abstains from giving a meaningful conjecture. It is also allowed. Okay, so this is the learning domain, the hypothesis space, and a learner. So a learner is just a function, and here I should note that we don't really talk about its Turing complexity of this function. Okay, so here I can reiterate what is a learner, and the learning is declared successful if what happens? For every structure from the learning domain, if it is an isomorphic copy of the structure AI from our family, then in the limit, the learner should stabilize. That is, we feed the learner like longer and longer initial segments of our structure S. So this limit should stabilize. Okay, so there is a finite limit, and this limit precisely is precisely the correct conjecture. That is, we guess that this structure is an isomorphic copy of AI. Okay, so that's it, and the final definition is like that. Our family K is learnable up to isomorphism, of course. because we guess the types of structures like up to isomorphism type. If there is a learner M that successfully learns the family K. Okay, so this is the formal definition of our paradigm. And there is some small footnote that more formally we should be more careful and we should say that more things. This is, formally speaking, inf x isomorphism learnable. So isomorphism, of course, because we learn up to isomorphism, because as Katya Fokina said on Monday, we can learn structures up to other equivalence relation, for example, up to bioembedability relation. But here we only concentrate on the isomorphism. So that's why I omit this subscript isomorphism. But more importantly, there are also two modifiers. So inf means learning from informant. A learner M obtains both positive and negative data from the atomic diagram of a structure. And as typical in the algorithmic learning theory, you can imagine other modes of information. For example, we can get only positive data from the structure or from the atomic diagram, only negative data or something even else. Yes. Okay, so here we obtain all data. And X means explanatory. So this is about the particular success criterion. So we declare explanatory learning is successful if in the limit we converge to this particular correct conjecture. There are also stronger and weaker, in general, success criteria. But we won't talk about these criteria, I think, up to the last slide of the talk. So for now, we can forget about this footnote. And our main learning paradigm is this one. We always learn up to isomorphism, and the learning is successful if in the limit we will always output the correct unique conjecture. Okay, so this is the formal definition of the paradigm. Okay, and in 2020, together with Katya Fokina and Lucas Anmauer, we obtained the following result that this learning paradigm, it admits full syntactic characterization. So the theorem states the following. We consider a countable family of countable structures. Then the family is learnable if and only if there are infinitary sigma 2 sentences psi I with the following property. So I will say it less formally. Inside the class K, each structure is distinguished by its own infinitary sigma 2 sentence. So for AI, the only sentence which is true, that is the sentence psi I. And all other sentences psi j are not true. So within the class, there is some infinitary sigma 2 property which distinguishes only this structure. And this is for each of the structures AI. Okay, so this is kind of a purely syntactic or model theoretic characterization. And when we have this characterization, more or less, in some cases, we can forget about even the original definition of learnability, and we can work purely syntactic. And this is very useful for some familiar algebraic classes. For example, using the description of infinitary sigma 2 types for linear orders, which is given by Montalban in his 2010 paper, we can prove that using this syntactic criterion that there are no learnable infinite families of linear orders. So, and this is sharp because for any finite number k, of course, finite non-zero number k, there is a learnable family of computable linear orders of cardinality k. So of any finite size, one can build a learnable family of linear orders, and there are no learnable infinite families of linear orders. So this is okay. So, and also, for example, for Boolean algebras, the learning becomes trivial. One cannot learn even a pair of non-isomorphic Boolean algebras. Okay. So And if we go further, one interesting question is the following. We briefly touched it in our previous works. We can play in some numbering theoretic fashion with the hypothesis space HS of K. And this is also typical, I believe, for the classical algorithmic learning theory. First, we can remember that when we talked about our family of countable L structures, we did not talk about the complexity of the structures, and we also did not talk about the complexity of the list of the structures. And of course, we can introduce some restrictions. We can say, okay, our list of structures should be uniformly computable. Okay, so this is kind of a restrictive condition. But on the other hand, we can relax some other condition, and this is kind of a typical number theoretic thing. We can say, okay, now our list could contain repetitions, because remember we said, okay, so these AIs, they all have pairwise different isomorphism types, but now we could say, okay, we don't care about this. It could be the case that for different I and J, the structures are isomorphic. And unfortunately, not much is known in this direction. We can here give only one result. If we consider finite learnable family of structures, then this becomes kind of more or less absolute result. That is, we don't care too much about the hypothesis space is arranged, what is the numbering of our family of the structures, etc. In a sense, we don't care much about this. And if we have a finite learnable family of computable structures, then it will be always learnable by a zero-jump computable learner. Okay, so there's this whole direction of the learnability, say the Turing complexity of learners, and how it would depend on the arrangement of the hypothesis space, how it would depend on the particular numbering in which we organize the hypothesis space. Okay, so and if you think about this, one can say, okay, in a way, this direction is more or less over, because, okay, now we have nice enough syntactic characterization, and that's it, and all boils down to syntactic things, and what is the point of this talk, etc. But of course, here comes like here where the talk really starts. Where do Borel equivalence relations come from? Okay, so, and the rest of the talk is a joint work. All results are joint work with Vittorio Cipriani and Luca Sanmauer. Okay, so let's look again at the syntactic characterization. I just wrote down the same theorem here again. And let's look a little bit at the proof of this theorem. So if we want to go from 2 to 1, then this direction is not so interesting. Essentially, roughly speaking, if we learned how to learn the pair of linear orders omega and omega star, then essentially the same algorithm or the same idea of the algorithm works. If we want to prove to build from a sequence of infinitary sigma 2 sentence, how to build a learner for this family K. So from 2 to 1, it is not hard when we notice that omega and omega star is like the typical behavior of a learnable family. Okay. But the other direction, from 1 to 2, is much more interesting, and we will see what happens here. The king gradient of the proof, essentially all the hard work was done before us. So the key ingredient is the relativized version of the pullback theorem of Knight, Sarah Miller, and Vandenboom, published in 2007. This theorem it gives some syntactic facts. For now, it is not important what it talks about, but more important that it talks about Turing computable embeddings. So in Russell Miller's talk on Tuesday, he already talked a little bit about Turing computable embeddings. So what is it? We have two classes of structures possibly in different signatures. So one class is in one signature and another class is in another signature. And a Turing operator phi is a Turing computer embedding from the first class into the second one if it satisfies the following. Given a structure from the first class, phi a will be a structure from the second class, and this is an embedding. That is, uh, the operator phi works injectively on isomorphism types. Of course, isomorphic things goes into isomorphic things, and vice versa. Non-isomorphic things also go into non-isomorphic things. Okay, so this is the definition. And it is interesting, and we thought a lot about whether it is kind of really necessary in this proof, and is there a kind of some deeper connection to, say, descriptive set theory, etc. And it turns out that there is some connection. Okay. Let's go to the second slide. Here, as I said, the reduction emerged. Russell Miller, in his talk on Tuesday, discussed, provided a very good exposition about the reduction. Here I just only mention some definitions. So in general, a reduction reduces equivalence relation, one equivalence relation on some set to another equivalence relation on the other set. Okay. So, and in descriptive set theory, one typically takes x and y as Polish spaces, and if this reduction, this function is, sorry, here should be g, this function g, the same as here, is Borel, then this is a Borel reduction, and if the function is continuous, then it is a continuous reduction. So, what happens? It turns out that here, in a natural way, continuous reductions emerge. Recall one of the benchmark Borel equivalence relations on the counter space, which was also already introduced in the talk of Russell Miller. This is the relation of eventual agreement of reals. That is, two reals are zero equivalent. If starting from some bit, they're just the same. And also our learning domain, the set of all isomorphic copies of the structures from our class is a subset of counter space, of the counter space. So, and if one looks at the syntactic characterization, that's what can be obtained. Again, we consider a countable family of countable structures. Then the family is learnable if and only if there is a continuous function gamma acting from the counter space into the counter space, cited for all structures from the learning domain. That is, this is a subspace of the counter space. We have the following. The structures are isomorphic if and only if the images are zero equivalent. And this is a criterion. So, in other words, the second item, item B, says what? Modulo some technical details. Okay, we have a continuous reduction from the restriction of the isomorphism relation to the copies of structures from our class K to the benchmark Borel equivalence relation is zero. So kind of maybe a little bit surprisingly, we discovered this natural connection of learnability with a descriptive set theoretic notion. But okay, when you already see this formulation, and if you think a little bit about this, then in fact you can see that this is not that surprising, because kind of roughly speaking, learning is a delta 2 process and it should converge. So in a way, up to finite number of bits, we should converge to some particular real, and these reals are not zero equivalent. So if you think more about this formulation, this becomes kind of more natural and maybe less surprising. Okay, so this is the first theorem. We obtained this a little bit unexpected connection to a benchmark barrel equivalence relation. And this motivates us to give a kind of natural definition. Okay, so now we can talk about any essentially equivalence relation on the contour space. And we can define the notion of learnability with the help of this relation E. And essentially, we just copy the second item of the previous theorem, but we replace the relation E0 with our given relation E. That's what it happens. So there is a continuous function gamma from the contour space into the contour space, such that for all structures from the learning domain, the isomorphic if and only if the images under gamma are equivalent with respect to E. So this is just the copy of this second item. And essentially, this could be treated as an approach, a descriptive set theoretic flavor approach to expansion of our learning power. How can we classify up to learning the non-learnable families? Because you already saw that learnable families in the classical sense, they're kind of pretty restricted model theoretically. Okay, and of course in general, because in this definition, it is not necessary to require that the family K is countable, because of course it could be uncountable. So we could also consider elearnability for uncountable families, but we will not discuss it here. Okay. So the first example is kind of a natural one, and this is what you would expect. And this just illustrates that this approach really expands the learning power. So what can we do with this kind of natural? First, we identify the contour space with the space of all countable graphs via some particular encoding. And then we can define the following equivalence relations on the contour space. For a non-zero countable ordinal, we say that two reals are R lambda equivalent if and only if the corresponding graphs satisfy the same infinitary sigma lambda sentences. So kind of the graphs have the same infinitary sigma lambda theories. And this is not surprising, and in fact, all the preliminary work was kind of maybe a little bit surprisingly already done in some previous paper of mine, that if we have this particular kind of natural equivalence relation, then we can obtain a full characterization of learnability. So the families are lambda learnable if and only if, like, in the same flavor, in the same taste as the original characterization of Fokinas and Maurer and myself. This is the same. For each structure AI, there is its own infinitary, now it is sigma lambda sentence, which distinguishes this particular structure from all other structures in the class. So within the class, each structure is distinguishable by its own infinitary sigma lambda sentence. Okay, so, and of course, this gives some kind of, I don't know, a hierarchy of a countable hierarchy of learnable power, etc., which of course strictly grows as the ordinal grows. Okay, this is just the first example, and we just transfer the original characterization to some other natural barrel equivalence relation. Okay, and our second step, yes, thanks to Russell Miller, you have already seen this picture in his talk on Tuesday. So, as a case study in our work, we considered the benchmark barrel equivalence relations. And these equivalence relations are precisely the same as in Russell Miller's talk. And I will only say a couple of things before I proceed. So Russell's yes. So the point is this: this is the picture not only up to barrel reductions, but it is also a picture up to continuous reductions, because these arrows, for example, E0 is reducible to E1 via continuous function. So in fact, all these arrows which exist are continuous reductions, and the non-existent arrows say that there is no barrel reduction. Okay, so this is my first comment. So these all reductions are continuous, like these arrows. And also, I should note some difference. By ID, we denote the identity relation, and we denote the nth column of a real by alpha with a superscript m in square brackets. Okay, so these are kind of the benchmark barrel equivalence relations, and this is their picture up to continuous reductions. And why are continuous reductions are more important for us? Because one can easily see, and this is kind of an immediate consequence of our definition of learnability, that if E is continuously reducible to F, then every E-learnable family will be also F-learnable. So if you have some continuous reduction, then automatically this implies kind of this comparison of learnability power of these two relations. So for example, every E0 learnable family is E2 learnable. Okay, so that's why continuous reductions here are important for us. Okay, so and the second question that could arise: okay, is this definition, is this our definition of e-learnability a natural one? So because you can say, okay, you just copied and pasted the second item of your theorem, and why does it make it the things natural? There is at least some arguments to this, because for at least one benchmark equivalence relation, we could obtain a kind of a natural syntactic characterization, also in the vein of the very first theorem of Hawkins, Hammer, and myself, which goes through, this characterization goes through. So E3 relation is what? So two reals are E3 equivalent if all the columns, nth columns, are E0 equivalent. Okay, so this is just the definition. And one can obtain a syntactic characterization of E3 learnability. The family is E3 learnable if and only if, okay, I would like to try to introduce this notion slowly, because it is kind of natural, but it's not that straightforward. So there exists a family of infinitary sigma 2 sentences with the following properties. First one: inside the class, all of the sentences are kind of infinitary delta 2 definable. What does it mean? So for every formula from this family, there is another formula, sigma 2 infinity formula, again from the same family, such that inside the class, that is for every structure from the class, we have theta holds if and only if the negation of psi holds. That is, each of the formulas from this family can be rewritten inside the class as an infinitary sigma 2 formula, and also as an infinitary pi 2 formula. So kind of each of the formula has an infinitary delta 2 definition. This is what I mean here by that. Okay, so kind of a specific family of sentences. Okay. And more importantly, how it is connected to our family, how these formulas theta are connected to our family. For each pair of different indices, I not equal to j, there is a particular formula from this family such that it is true in the structure AI and it is false in the structure AJ. This is some kind of I would say maybe a Hausdorff kind of property or something like that. So each pair of different structures AI and AJ can be separated by a particular pair of formulas, and each of the formulas are kind of delta infinity or delta 2 definable inside the class. This infinity or delta 2 definability I already explained what it is. Okay. And this is the criterion. So kind of maybe it's not the easiest or the simplest criterion that you have seen, but in a way it is natural criterion. It says about existence of some particular or nice families of formula which separate structures pairwise. So this is different from the first criterion because the first criterion just one formula separated one structure from all other guys. And here it's kind of not like that. It's every pair of structures is separated by its own pair of formulas. This is kind of this criteria. One can say that E3 learnability, in a sense, this is also a natural notion which admits a nice syntactic characterization. Okay, this is good. So, and immediately, if we have a syntactic characterization, then using the syntactic characterization, remember that for E0 learnability, we also have syntactic characterization. We can immediately obtain that every finite E3 learnable family is already E0 learnable. So for finite families, E0 and E3, the learning power is just the same. But there is an infinite E3 learnable family, which is not E0 learnable. Okay, so the learning power is different. In general, is different. All right. So here I stated the same corollary again. And when we obtain this result, it is kind of natural to introduce or to define new learning-related reducibilities. So, and these are kind of essentially motivated by this corollary. So we have two equivalence relations on the contour space, and we say that E is learn reducible to F if every countable E learnable family is also F learnable, and E is finitely learn reducible to F if every finite E learnable family is also F learnable. And from the definitions, it is clear that continuous reducibility between E and F will imply learn reducibility, and this will imply finitary learn reducibility. So these reductions are weaker in general than continuous reducibility. And then we just reformulate our corollary. Essentially, what we obtain that for finitary learning power, E0 and E3 are just the same, as I said, and for countable learnable power, E0 is strictly below E3. So, and for example, this example shows that this arrow does not reverse. So from this reduction, we cannot in general obtain this reduction, okay, because E0 and E3 are equivalent, but here they are not equivalent. Okay. So we obtain these results. And so what did we obtain for other benchmark equivalence relations? For finitary learn reduction, for this particular benchmark equivalence relations, we obtained a full picture. So these guys just form 3 degrees. So this is the identity on reals. E0, E1, E2, E3, Z0, they collapse to the same degree. Yes. And E set is strictly above this degree. And in order to distinguish E set from all the other guys, it is really simple, because the family of 2 linear orders omega and the order of integers. This is that learnable. It is not hard to prove, but it is not learnable in the classical sense that it is not E0 learnable. So this is also a natural example which separates these two degrees. Just in case, I reiterate the picture up to continuous reductions. So up to continuous reductions, all this complicated, there's this complicated picture, and up to this reduction, it collapses just in a linear order. And also, for completeness here, I give this picture that was, I believe, already shown in Russell-Miller's talk about computable finitary reductions. The picture also looks like this. There is this linear order of 3 degrees for this same barrel constellations. But on the other hand, our reduction is kind of different because somehow the relations are grouped in different degrees. So here are 3 relations above, 3 relations in the middle, and here somehow only 1 relation above and all 5 relations in the middle. So this is a different reduction than the finitary computable reduction from defined by Russell, Miller, and Kahneman. Okay, so and yes, I am already finishing. Up to learn reduction, I remind the definition again here. Unfortunately, first, we don't have a complete picture here. We still could not prove what happens with the degree of Z0. And Z0, remember, is this guy alpha and beta Z0 equivalent if the asymptotic density of the symmetric difference of alpha beta is 0. So we still could not locate what happens with this degree, but modulo this guy, again, we have a complete picture. This is a linear order consisting of 4 degrees, and here E0, E1, and E2 collapse. And E3 now separates from this guy, and also E set is already separated. And again, if you remember the picture of barrel embeddings, it shows that in general, this learned reducibility does not imply barrel reductions because all these guys are equivalent, but up to barrel reductions, they are separate. Okay. So, and here again, I give this picture. Again, this is the previous theorem. This is the same picture on the continuous reductions. And here's this interesting moment because we could not locate where Z0 lies. But if we consider the countable computable reduction of Russell, Miller, and Kahneman, this is from the paper of Russell, Miller, the picture kind of looks the same. Russell Miller proved that Z0 is also equivalent here to E3, and we don't know whether it is Z0 here is equivalent to E3. And kind of, I'm very interested, are these pictures are really the same or not? Because kind of, it seems that the methods of Russell, Miller, at least both these definitions, they do not straightforwardly imply each other. Like so, they seem kind of independent, and the methods of Russell, Miller do not directly translate into our setting. So it would be interesting if somehow these 2 pictures are really the same, and for some deeper reason that we still fail to see somehow. Okay, so this is kind of yes. So this is kind of interesting. Okay, so and I'm finishing. So there are the last 2 slides. So further problems that are left open. So first 2 are immediate problems. We still did not manage to locate the degree of the benchmark relation Z0. And in the same vein, one can consider other popular benchmark parallel equivalence relations. For example, Turing equivalence of reals, M equivalence of reals, like recursive isomorphism of reals, etc. For example, these recursion theoretic equivalence relations. And can one obtain a nice enough, in some way, syntactic representation of ESET learnability? Because remember that this ESET guy is like the top one. This is the most powerful among our other benchmark relations, and we still did not obtain a nice syntactic characterization of learnability up to this guy. And also, of course, this can be extended to, say, learnability for Turing equivalence or something like that. Okay. So, and another question which I think opens quite a wide line of research. This is what I promised in, I think, in the middle of my talk, to talk a little bit about other learning paradigms. Can we obtain similar descriptive as theoretic characterizations for other learning paradigms? And here I give just one example, one preliminary result that we managed to obtain. There is this kind of a stronger learning notion. What does it do? We say that a family is infin learnable. So inf again learning from informant, and fin means finite here. If this learnable, like in our usual, if our usual classical setting by a learner M, but this learner M satisfies an additional property. If a structure S is isomorphic to one of our benchmark structures AI, then there is some stage with the following property. Before this stage, we always abstain given a meaningful conjecture. But after this stage, we always output a correct conjecture. That is, M never ever says wrong conjectures. First, it abstains from giving any conjectures about our input. And from some point of time, it somehow immediately starts outputting the correct conjecture and never ever changes it. So it's kind of strong learning. So learning without essential mistakes, a stronger version. And it turns out that this notion also obtains a descriptive set theoretic characterization. So I will read this. A family is infinite learnable if and only if there is a continuous function from the counter space to counter space. The first item is just the same as in the definition of e-learnability, that is A isomorphic to B if and only if the images are equal, just equal. But there's another additional topological condition. The range of this gamma, or wait, more correctly it is to say the image of the learning domain relative to gamma, this is more correct. It should have no limit points. And this is a criterion. So infinite learnability is just the same as learnability up to the identity relation with the additional topological property. The range has no limit points. So in this sense, we have some hopes that at least some stronger notions of learnability could also obtain a kind of a nice descriptive set theoretic or topological characterizations. Okay. So that's all. Thank you for your attention.
Thank you very much, Nikolay. Anybody have any questions? Jun Lee.
Thanks, Nikolay. Just a couple of questions about basic definitions. Can you go back to the definition of learner at the beginning? Like slide 6 or something.
Okay. Okay. Yep.
Yeah. Okay. Thanks. So, for the setting of like inf x, so for most of your talk, am I right to say that the question mark actually doesn't matter? Like we could just say the question mark is 0.
Yes, precisely. You are right.
Okay.
It only matters in the in this infin learnable because
Yeah.
yeah, okay.
Right. Okay. Cool. And also, can you go to the e-learnability definition again? I just didn't read it carefully, I think.
Yeah.
Great. Thanks. So I'll pass it on.
Question from Stefan. Let me walk the mic up here. Go ahead, Stefan.
Thanks, Kolya. Nice talk. I have two related questions. You have this condition that the AI and AJ for distinct I and J always have to be non-isomorphic. How important is that condition ever important? And if it is important, can you fix it by going from explanatory to PC learning?
Okay, so I think the point is if we do not care about the complexity of a learner, it is not important because if we have some enumeration and if we don't care about the complexity of the enumeration, we can always recover Friedberg enumeration up to isomorphism from this. So if we talk only about continuous setting, this is not important. This becomes important when we care about the Turing complexity of the learners. Does it answer your question?
Yeah, thanks.
Yes, thank you.
Question from Uri next.
Thank you, and nice talk. My question is about this definition of e-learning here. In the E0 setting, you just said that the question mark doesn't matter because you can just say 0 for a while, but potentially in other relations you might use there instead of E0 learning, could that matter? And if so, I guess I'm wondering about, right, you're demanding a continuous function on all of Cantor space, not just that the function be continuous on the learning domain, and does that make a difference?
Okay, thank you. So I think I will start from the second question. Here we require, yes, really a continuous function on the whole Cantor space, and in a way, this is kind of how to say this, a remains of the learning paradigm. Because if I go again back, here we also require that the learner M is a function from the whole set of finite strings into hypothesis spaces. So if we define for E0 learnability, yes.
Right, but he's allowed to say question. The question mark is allowed, right?
Yes, the question mark is allowed. And I believe in general, for e-learnability, question mark is not that important because we always require that for the correct input, we will eventually see like the correct conjecture. So this means that we can, as Junle said, safely replace question mark with 0. Yes, in the setting of learnability, and just delete this question mark.
Right, but for incorrect inputs, things that are not in your learning domain, does that have any effect on the continuity in your definition of e-learnability?
This is a good question. Yes, I think that in general, this is a good question. I think that in general, you can also define that like a function to be partially continuous, yes? So that it would be defined only on the learning domain. This is what you mean, yes? And maybe in general, we did not think deeply about this. Maybe in general, this will give different definitions. But I believe that for benchmark equivalence relations, that we consider, because they are kind of very, how to say, tame. Yes, kind of tame. I think this does not matter whether here will be like a total continuous function or just a partial continuous function, which is defined on the learning domain. I believe in general. It also depends on kind of a particular family. Well, now, okay. So summarizing, I would say that this will make in general two different notions. If we require this as a total function on the counter domain or a function on the defined on the learning domain. But for the sake of the results which are in here, I think it makes no difference.
Great, thanks. We have some more questions in the room, but first, are there any questions from the online participants? Okay, so this is a question from Alberto.
Hi, very nice talk. I'm just wondering what is written in the remark there. I mean, obviously the definition of elearnability has no reason to stick with a family of countable structures. So do you have any results about the uncountable case, or well, obviously syntactic characterization probably is hopeless in that case, I guess.
We have only very preliminary results. We kind of conjecture that well, how to say this? In general, if we consider like arbitrary families up to continuum size, then maybe this will like this learn reducibility with respect to families of arbitrary size up to continuum could coincide with just the continuous reducibility. We kind of conjecture this, but we don't have a proof for this. That's why, yes. So, and in general, I would say, of course, like for uncountable families, like this. What was the point? This because our suspicion is like that, because for uncountable families, of course, all our proofs for collapsing different degrees into one, so say for example like this result that E1 and E0 are just collapsed up to countable families, they just don't work. Yes, so that's why we also conjecture that maybe learn reducibility up to arbitrary families could be just the same as continuous reducibility. Yes, and other than that, we have only preliminary results building some kinds of families which separate different themes, and that's it.
Thank you. Anything else? Okay, thanks so much.
Thank you.
That's the end.